Andromeda stands as one of the most fascinating and critical anomalies within the observable universe. Picture this vast cosmic expanse where nearly all galaxies seem to be drifting away from us, their light stretching into longer, redder wavelengths, a testimony to the relentless expansion of space-time itself. Yet amidst this grand exodus, the Andromeda Galaxy, also known as Messier 31 or simply M31, defies this universal trend. Unlike most of its cosmic neighbors, it is not pulling away but rushing straight toward us. This remarkable movement is far from just a curious oddity. It reveals profound truths about the nature of gravity, the limits of cosmological expansion, and the complex dance of galaxies in the local group. If we think about the universe as a vast stage where galaxies are performers, most are stepping backwards, moving away as the stage itself expands. However, Andromeda is sprinting inward, held tightly by the invisible strings of gravity that bind it to our Milky Way. But this gravitational grip is local and strong enough to overcome the large-scale push of cosmic expansion. This means that although space itself is growing larger everywhere, on the scale of galaxy clusters like the local group, gravity acts like a powerful anchor, pulling massive galaxies back together. Now let us talk numbers to ground this extraordinary story in reality. Current measurements place Andromeda approximately 2.5 million light-years from Earth. This is a colossal distance, about 765,000 kiloparsecs if you prefer astronomical units. What truly captures the imagination is its velocity as it approaches us. Astronomers have measured a heliocentric radial velocity of approximately negative 301 kilometers per second, where the negative sign indicates approach rather than retreat. To put it in perspective, that is nearly 90 times faster than the cruising speed of a jet airliner, and more than 250 times the speed of sound on Earth. This velocity translates roughly to 250,000 miles per hour, or over 400,000 kilometers per hour. The significance of this velocity extends beyond raw speed. It directly evidences the massive gravitational influence exerted by the combined mass of Andromeda and the Milky Way, dominated by elusive dark matter halos enveloping both galaxies. This mass overdensity exerts sufficient force to overwhelm the outward push of cosmic expansion, predicted by Hubble's law, which governs the overall recession of distant galaxies. Andromeda's motion toward us is a glowing demonstration, quite literally in the cosmic sense, of how local gravitational binding energy dictates the behavior of galaxies within a group, trumping the universal tide that draws more distant galaxies apart. For many decades, despite this known approach, astronomers hesitated to declare an unambiguous collision course between the two galaxies. The missing piece of the kinematic puzzle was Andromeda's proper motion, its lateral movement across the plane of the sky. While radial velocity tells us how fast it moves towards or away from us, proper motion reveals whether Andromeda might sweep past at a safe distance or curve around, avoiding a cosmic crash. Without precise data on this subtle sideways drift, scenarios range from a collision to a close but non-impactful encounter. The breakthrough came in the early 21st century, fueled by the incredible precision of the Hubble Space Telescope. Over nearly a decade, starting in 2002, astronomers painstakingly observed the positions of thousands of bright stars embedded within Andromeda, measuring their minute shifts against the faint backdrop of distant galaxies. This exhaustive effort employed advanced techniques to reduce noise and achieve stunning sub-pixel accuracy, culminating in a definitive proper motion measurement. The outcome was revelatory. Andromeda's sideways speed is minuscule, less than 1/10 of a millisecond per year. This tiny value means that Andromeda is not meandering across the sky, but is almost directly falling straight towards the Milky Way. This finding sealed the fate of the upcoming event. The eventual merging of these giants is statistically inevitable and highly likely to be a near head-on collision. The gravitational interaction between their massive dark matter halos guarantees an inexorable cosmic convergence. This is no mere flyby or gentle embrace, but a profound encounter destined to reshape the local group profoundly. The significance of confirming this collision extends far beyond academic interest. It represents a triumph of observational astronomy and technology, demonstrating how human curiosity, combined with modern instruments, can predict one of the next major events shaping our galactic environment billions of years hence. This cosmic countdown from the edge of the observable universe to our own cosmic backyard illuminates the power of gravity and the ever-evolving nature of the cosmos, reminding us that even on the grandest scales, the universe's story is written in motion, force, and fate. In sum, the Andromeda Galaxy's approach towards us is not just an isolated quirk, but a testament to the fundamental forces sculpting the cosmos. It sits as a cosmic herald, signaling enormous changes on the horizon. This dramatic journey and collision echo the intricate balance of cosmic expansion and localized attraction, echoing forces that will rewrite the galactic map long after our time. Understanding this motion invites us to witness the celestial mechanics at play and prepares us for the future legacy of the universe as two massive island universes converge into one. This foundational narrative builds the very framework for our story. It sets the cosmic stage upon which the epic dance of galaxies unfolds and highlights the triumph of human insight in glimpsing the future across unimaginable distances. With this confirmed collision as our compass, we move onwards into the details of Andromeda's role in expanding our cosmic horizons, its structural mysteries, historical cannibalistic past, and the dramatic aftermath that awaits the birth of a new galactic giant. Let this be our starting line. The cosmic countdown is in motion, and Andromeda's journey toward us marks the ticking of a universal clock, a compelling odyssey written in the language of gravity and light, drawing nearer with every passing year. The collision of Andromeda and the Milky Way is no longer speculation, but an approaching certainty that will redefine the landscape of our cosmic neighborhood in the epochs to come. We now proceed with anticipation and wonder, ready to explore the next chapters of this incredible celestial saga. The universe's grand narrative continues, and we stand at the cusp of understanding one of its most monumental events. From the earliest moments of cosmic observation, the question of the universe's scale has fascinated and puzzled humankind. Among the vast expanse of stars and nebulous swirls, one particular enigma sparked an epochal shift in astronomical understanding: the Andromeda Galaxy. Before its full nature was known, humankind found itself grappling with the limits of the universe and its own place within it. The profound impact of Andromeda's discovery does not merely stem from its physical presence, but rather from the transformative journey it inspired within scientific thought and cosmology. At the root of Andromeda's cosmological significance lies a conflict that forever marked the history of astronomy, famously remembered as the Great Debate of 1920. This public and intellectual controversy was not a mere squabble over classifications, but a fundamental struggle to define the very boundaries of the universe. Two eminent astronomers, Harlow Shapley and Heber Curtis, stood on opposing sides, each defending a radically different vision of the cosmos. Shapley, a towering figure in early 20th century astronomy, argued passionately that the Milky Way galaxy was essentially all there was to the universe. In his view, the Milky Way was an immense island of stars, immense enough to contain countless faint nebulae observed in the sky. These spiral nebulae, including what we now call the Andromeda Galaxy, were seen not as separate entities but as nearby clouds of gas or clusters within the Milky Way itself. Shapley's model placed our sun far from the center of this singular galaxy, stretching its boundaries vastly but still containing all celestial phenomena within its grasp. Curtis took a distinctly different stance in this debate. He contended that the spiral nebulae were not mere gas clouds, but rather entire galaxies themselves, island universes, comparable in scale to the Milky Way, but far distant from it. This implied an astonishingly larger universe composed not of one single galaxy, but a multiplicity of galaxies scattered across unimaginable cosmic distances. Curtis's argument was rooted in the observation of novae and other transient events within these nebulae, which appeared too faint to be within the bounds of the Milky Way, unless extraordinarily weak. The more logical explanation, he asserted, was that these structures were millions of light-years away. Though widely discussed and fiercely debated, this profound discord lingered unresolved for several years. Both Shapley and Curtis held valid points, but neither had definitive evidence capable of conclusively settling the issue. The cosmic stage was set for a breakthrough that would utterly transform our understanding of the universe's true makeup. The key to unlocking this mystery emerged through the dedicated work of Edwin Hubble, whose pioneering observations reverberate through astronomy to this day. Utilizing the powerful 100-inch Hooker telescope at Mount Wilson Observatory, Hubble sought a way to measure cosmic distances with greater accuracy. His tool of choice was the Cepheid variable star, a type of pulsating star whose brightness rhythmically varies in a way directly linked to its intrinsic luminosity. By observing the period of a Cepheid's pulsation, astronomers can reliably calculate its true brightness, and by comparing this to its observed brightness as seen from Earth, arrive at an accurate measurement of its distance. When Hubble pointed the enormous telescope toward the Andromeda Nebula, he discovered Cepheid variables embedded in its spiral arms. Carefully measuring the periodicity of these stars' light pulses, he astonished the world by finding that Andromeda was far too distant to be inside the Milky Way. Its stars were located millions of light-years away, beyond any plausible boundary of our home galaxy as then conceived. Through this groundbreaking evidence, Curtis's perspective was unequivocally vindicated, revealing the Milky Way as just one of countless galaxies forming the vast cosmic tapestry. The implications were staggering. The universe was no longer a single galactic island, but an archipelago of galaxies, each containing vast numbers of stars, gas, dust, and dark matter. Andromeda became the first clearly identified external galaxy, a luminous benchmark marking the horizon beyond our own cosmic neighborhood. This shattering of perceived limits propelled astronomy into a new age, expanding the scale of human knowledge in a single leap. Hubble's use of Cepheid variables laid the cornerstone for the cosmic distance ladder, anchoring measurements that would underpin the study of galaxy clusters, the expansion rate of the universe, and its very origins. The precise distances inferred from Cepheids became calibration points, enabling astronomers to refine their models of the cosmos and piece together its grandest mysteries. Measuring the distances to other galaxies like Andromeda opened pathways that eventually led to discoveries about dark energy, the Big Bang, and the large-scale structure of the universe. This story of Andromeda's discovery and its transformative impact reveals how science evolves through challenges to establish truths. It demonstrates the power of careful observation, technological advancement, and bold theorizing. Andromeda, once a faint spiral nebula, emerged as a revelation that expanded humanity's horizon and forced a dramatic rethink of our cosmic context. Importantly, Andromeda's dual role does not end with its contribution to our understanding of scale. This same galaxy, revealed to be an immense island universe, is now known to be on a collision course with our Milky Way. The interplay of its past significance and future destiny enriches the narrative, illustrating how cosmic entities serve multiple roles across time in shaping knowledge and reality. As we consider Andromeda's great debate and Hubble's decisive measurement, it is crucial to recognize this moment as the foundation upon which much of modern astrophysics is built. From the debate arose a richer picture of the universe as an interconnected web of galaxies rather than a solitary island. The expanded framework sets up all that follows: Andromeda's structure, its peculiar double nucleus, its cannibalistic history, and the dramatic merger that lies ahead with our own galaxy. With a sound footing in Andromeda's historical and cosmological importance, we are prepared to explore its detailed physical characteristics. We will delve into what makes it unique within the galactic population, examining its vast size, stellar population, enigmatic core, and halos brimming with the remnants of past galactic encounters. This understanding enriches our fuller appreciation not only of Andromeda's scale and past, but also of the dynamic future journeys toward the spectacular union of the titans of our local group. In this way, the great debate and the triumph of Edwin Hubble's observations form a vital link in the grand narrative we are unfolding. It is a story of discoveries, curiosity, evolving knowledge, and the ever-expanding universe, just as inexorable as the migration of Andromeda itself toward the destiny that awaits. The Andromeda Galaxy is nothing short of a colossal titan in our cosmic neighborhood. Its sheer scale and intricate structure set it apart as a subject of vigorous study among astronomers, but its mysteries run deeper than size alone. Understanding Andromeda's shape, core, mass, and the interplay of its components brings us closer to grasping the dynamics not just of a single galaxy, but of the grand cosmic forces shaping the universe. To start, Andromeda is classified as a barred spiral galaxy of morphological type SASB. This classification tells us that it sports a prominent central bar structure, with sweeping spiral arms extending outward in an elegant spiral fashion. These arms are home to billions of stars, gas clouds, and nebulae glowing in a spectacular celestial display. When compared to our own Milky Way, Andromeda stands as the largest spiral galaxy in the local group, shining with an estimated stellar population of around 1 trillion stars. The galaxy's diameter extends approximately 152,000 light-years, making it significantly larger than the Milky Way's roughly 100,000 light-year span. This vast expanse is a testament to Andromeda's dominance in size and matter within our local cluster of galaxies, but it also invites questions about the mass distribution that governs its motion and the fate of its impending collision with the Milky Way. Central to Andromeda's intrigue is its nucleus, which defies simple explanation and showcases an unusual complexity unseen in many other galaxies. At the very heart lies a double nucleus consisting of 2 distinct concentrations named P1 and P2, separated by about 4.9 light-years. This configuration puzzles astronomers because while P2 is dimmer, it serves as the true gravitational center and houses the galaxy's supermassive black hole. P1, conversely, shines brighter but does not host the black hole. This apparent contradiction led to intense investigation, and eventually to a sophisticated model proposed by astronomers Tremaine and Paris. Their explanation reveals that P1 is not an independent object, but rather the collective brightness of stars orbiting the central black hole on highly elliptical orbits. These stars linger at the apocenter, which is the farthest point in their elliptical paths around the black hole, causing a photometric enhancement that gives rise to the illusion of a brighter secondary nucleus. This phenomenon highlights the intricate orbital mechanics and gravitational influences at play in the central regions of massive galaxies, painting Andromeda's core as a dynamic, finely tuned dance of stellar bodies. Moving beyond the nucleus, Andromeda's mass remains a fiercely debated topic in astrophysics. Traditionally, it was assumed to outweigh the Milky Way by between 25 and 50%, affirming its position as the local group's gravitational heavyweight. However, recent advances in dynamical modeling and observations of halo stars challenge this assumption. Studies focusing on the escape velocities of stars in Andromeda's halo have led to revised mass estimates, suggesting a virial mass closer to approximately 0.8 trillion solar masses, with a virial radius around 240 kiloparsecs. This downward revision brings Andromeda's mass much closer to that of the Milky Way, hinting that these two giants might be closer to parity than previously believed. This new mass perspective has profound implications for the dynamics of their eventual collision, indicating a more intense and symmetric merger rather than a simple dominance of one galaxy over the other. More intriguingly, this lower mass estimate places Andromeda as an outlier in the commonly accepted lambda cold dark matter cosmological model. Specifically, it challenges the expected relationship between stellar mass and dark matter halo mass, opening fresh questions about the galaxy's formation and dark matter distribution. The outskirts of Andromeda tell yet another story, one of a galaxy actively shaped by its history of mergers and accretions. The galaxy's stellar halo extends into the farthest reaches where it reveals a rich and frothy substructure. Surveys like Pan-Andromeda Archaeological Survey have mapped this halo in exquisite detail, uncovering a network of stellar streams and debris. These streams are remnants of smaller satellite galaxies previously devoured by Andromeda's tidal forces. Remarkably, 86% of the metal-rich stars in the halo reside in these streams, a vivid sign of Andromeda's past as a cosmic cannibal. In contrast, the oldest, most metal-poor stars form a smooth and spherical halo component with slight prolate ellipticity. This ancient stellar population's spherical distribution provides crucial clues about the dark matter halo enveloping Andromeda. Since dark matter dominates a galaxy's gravitational potential, its shape influences stellar orbits on large scales. The nearly spherical geometry inferred supports models where dark matter halos exert a stabilizing influence, anchoring the structure despite ongoing galactic interactions. To summarize, Andromeda's physical profile intertwines colossal size, intricate inner structure, and a complex mass distribution that challenge our models and inspire new research. Its barred spiral form frames a galaxy brimming with stars, order, and dynamic gravitational forces. The double nucleus showcases extraordinary orbital mechanics in the innermost regions, while evolving mass estimates refine our understanding of its role in the local group. Its outer halo serves as a stellar fossil record of accretion, revealing a violent past of hierarchical growth. These features not only deepen our appreciation of Andromeda as a unique and powerful celestial system, but also prepare us to understand the forthcoming milestone, the collision with the Milky Way. The galaxy's morphology, mass, and complex halo structure directly influence how these titanic encounters will unfold and redefine our cosmic neighborhood. By illuminating the physical details of Andromeda, we gain insight into the forces that will shape the future of the local group as these giants merge. Building on this understanding of Andromeda's anatomy and mass, we will next explore evidence of its past galactic cannibalism. Telltale scars etched on its halo as a vivid archaeological record. Through this cosmic archaeology, we uncover the history of interactions that sculpted Andromeda and foreshadow the patterns of destruction and creation expected in the Milky Way's impending future. The future of the Andromeda Galaxy and the Milky Way unfolds as one of the grandest cosmic dramas ever envisioned, a titanic dance of massive galaxies destined to collide and merge, reshaping the local group and the very face of our cosmic neighborhood. But like all great epics, the story is nuanced, and recent scientific advances have painted a far richer and more uncertain picture than given by earlier certainties. For decades, astronomers accepted the narrative that Andromeda and the Milky Way were on a near-certain collision course. Approximately 4 to 5 billion years from now, it was predicted that these two great spiral galaxies, the largest members of our local group, would come together in a colossal galactic merger. This anticipated encounter promised to transform both galaxies fundamentally, unleashing starbursts, reshaping their stellar populations, and ultimately giving birth to a new elliptical galaxy known colloquially as Milkomeda or Milkdromeda. The inevitability of this fate hinged on a key technological breakthrough, measuring Andromeda's proper motion, its sidewise velocity relative to the Milky Way. Without this, astronomers could only observe Andromeda's closing speed toward us, a Strong's blue shift indicating approach. The proper motion determined by the Hubble Space Telescope showed it to be incredibly small, meaning the galaxy's trajectory was nearly direct, making collision highly probable under earlier assumptions. However, as our tools and data have grown more sophisticated, especially with inputs from the European Space Agency's Gaia Observatory, a more complex reality has emerged. Recent studies incorporating precise measurements of galactic motions, masses, and gravitational influences from other local group members, such as the Triangulum Galaxy and the Large Magellanic Cloud, have refined the predicted outcomes. Recent research places the likelihood of a Milky Way Andromeda collision at about 50% within the next 10 billion years. Effectively a cosmic coin flip. It is no longer scientifically accurate to speak of the collision as a foregone conclusion, but rather a significant possibility balanced by alternative scenarios where the galaxies may pass close without merging. These nuanced predictions arise in part due to revised mass estimates and an improved understanding of dark matter halos that shape orbital dynamics. Should the collision occur, models suggest it will be a turbulent and transformative event spanning billions of years. The galaxies will not smash together in a simple crash, but instead undergo a complex and multi-pass gravitational interaction. Their spiral disks will be violently disrupted, triggering shock waves compressing vast clouds of interstellar gas, igniting intense star formation episodes known as starbursts. These periods will birth waves of massive new stars and set off supernova explosions, seeding the galaxy with heavy elements. Throughout this cosmic turmoil, direct collisions between individual stars remain exceedingly unlikely due to the enormous spaces separating them. The fate of the solar system in such a merger is uncertain, but modeled with probabilities. There is roughly a 50% chance that our solar system will be flung into a more distant orbit around the eventual merged galaxy's center, moving to as much as 3 times its current distance from the core. More dramatically, there is approximately a 12% chance of ejection entirely from the galaxy, becoming a rogue star system wandering the vast intergalactic void. Over the next 5 billion years, simulations predict that after a series of encounters and separations, the final coalescence will form a single, stable, elliptical galaxy. This galaxy, Milkomeda, will likely exhibit less rotational momentum and organized structure than the progenitor spirals, evolving to resemble the elliptical giants observed elsewhere in the universe. Accompanying this transformation will be the merger of the central supermassive black holes of both galaxies into an even more massive gravitational nucleus. An event with profound energetic consequences, including the emission of gravitational waves rippling across the cosmos. It is important to contextualize this event within the broader timeline of Earth's future. While the merger hints at a cataclysmic reshaping of galactic structure, Earth's fate is sealed independently by the natural evolutionary cycle of the Sun. Long before the intense tidal forces from Andromeda distort our galactic environment, the Sun will age into a red giant and render Earth uninhabitable. Therefore, for the human story and terrestrial life, the collision remains a distant and largely theoretical future. Thus, the unfolding story of the Milky Way and Andromeda intertwines certainty and uncertainty, cosmic scale and local fate, violence and creation. These galaxies stand at the crossroads of expansive cosmological forces, and their potential collision serves as both a symbol of cosmic grandeur and a laboratory for understanding galaxy evolution. Whether they collide or graze past, their gravitational interplay will define the coming epochs in the local group, ushering in a transition from the era of spirals to that of ellipticals. As we conclude this chapter of the saga, we look ahead to examining the aftermath and legacy of this galactic union, the birth of Milkomeda, and the shifting starscape destined to follow. The past and present converge in a future shaped by gravity's relentless pull, reminding us of the dynamic, ever-changing cosmos in which our own story unfolds. The cosmic countdown continues, marked by uncertainty, wonder, and the profound influence of galaxies destined to dance for billions of years to come. The powerful and often dramatic story of the impending galactic encounter between the Milky Way and the Andromeda Galaxy has captivated scientists and the public alike for decades. Yet recent advances in astronomical observations and modeling have introduced new layers of complexity into this cosmic saga, fueling a re-evaluation of what was once thought to be a near-inevitable collision. The tale of these giants is no longer a foregone conclusion, but a story enriched by uncertainty and nuanced possibilities. The classic scenario, long ingrained in scientific literature and popular imagination, focused on a catastrophic head-on collision expected to occur roughly 4.5 to 5 billion years from now. The evidence for this dramatic fate was strongest after precise measurements of Andromeda's blue-shifted velocity toward us and the tiny proper motion confirming that the galaxy was moving almost directly inward rather than sweeping by. Under this assumption, computer models predicted a sequence of transformative events. The galaxies would pass through one another, creating tidal tails, triggering bursts of star formation, and ultimately merging within billions of years to form a massive elliptical galaxy known colloquially as Milkomeda. However, as astronomers gathered more precise data from missions like the Gaia satellite and refined mass estimates, this once anticipated inevitability has become more balanced with alternative outcomes. Crucially, the gravitational influences of other key players in the local group have been incorporated, altering the dynamics significantly. The Triangulum Galaxy, a smaller but still substantial neighbor, exerts a gravitational nudge that encourages merging, while the Large Magellanic Cloud, a massive satellite of the Milky Way currently in the process of falling into our galaxy, acts contrary, deflecting the Milky Way's motion away from Andromeda. This gravitational interplay reduces the likelihood of a direct collision. Recent research suggests that rather than a near certainty, the chance that the Milky Way and Andromeda will collide within the next 10 billion years is close to 50%, a cosmic coin flip by galactic standards. This shift arises from integrating the latest three-dimensional kinematic data of stars, updated mass profiles of each galaxy, and the gravitational tug from significant satellite galaxies. It highlights just how sensitive galactic futures are to even slight shifts in velocities and mass distribution. If the collision does happen, the process will be far from a violent stellar crash, despite dramatic imagery often shown in documentaries. Galaxy collisions are primarily gravitational events involving the interaction of vast clouds of stars, gas, and dark matter. Stars themselves, separated by such immense distances, almost never collide directly. Instead, the galaxy's gravitational fields intertwine, profoundly disturbing their structures. The initial encounter will stretch and warp the delicate spiral arms of both galaxies and compress extensive molecular gas clouds. These shocks ignite spectacular, though chaotic, star formation events known as starbursts. New stars and possibly new planetary systems will light up parts of the evolving system. The merger sequence is predicted to unfold over several billion years, with the galaxies passing through one another multiple times, slowing due to dynamical friction between their dark matter halos until they settle into a merged entity. This final form, Milkomeda, is expected to be a large elliptical galaxy, shaped by the randomized stellar orbits and depleted gas reservoirs following the turbulent past. At its core, the supermassive black holes from both progenitor galaxies will spiral inward and coalesce, likely emitting powerful gravitational waves marking the merger's energetic climax. The long-term dynamical consequences extend even to our own solar system. Powerful computer simulations estimate there is approximately a 50% chance the solar system will be displaced to an orbit roughly 3 times farther from the galactic center after the merger. More drastically, there is around a 12% chance it might be ejected entirely beyond the merged galaxy, becoming a lone wanderer in intergalactic space. These outcomes illustrate the profound reach of galactic gravitational perturbations, without implying any immediate danger to the solar system's internal dynamics. On the flip side of uncertainty is the possibility that the Milky Way and Andromeda will not merge in the foreseeable future. Instead, they could enter a gravitational dance, orbiting each other for billions of years without ever fully merging. This outcome would still represent a massive reshaping of the local group, but would preserve both spirals as intact galaxies. Such scenarios challenge older models and emphasize the crucial role of continued observational refinement. Furthermore, the timeline itself remains subject to revision. While early estimates place the collision roughly 4 to 5 billion years ahead, newer models allow for a more extended interaction period, possibly delaying coalescence to 7 or 8 billion years or beyond. It is important to situate this galactic drama within the context of Earth's future. Long before Andromeda's tidal forces become dominant, the Sun's life cycle will drive Earth into inhospitability as it expands into a red giant and dramatically alters the inner solar system. The galactic merger remains a majestic event on timescales beyond direct human consequence, but essential for understanding cosmic evolution. The Andromeda Milky Way narrative is a testament to the evolving nature of scientific knowledge. It demonstrates how incremental improvements in data, advances in telescope technology, and sophisticated computer simulations continually reshape our cosmic understanding. Rather than a fixed story, the fate of these galaxies is a dynamic question, reflecting the interplay of gravity, momentum, and chance on the largest scales. As we look forward to the coming eons, the saga of Andromeda and the Milky Way exemplifies the grandeur and mystery of the universe. Whether colliding or entwined in a distant cosmic ballet, these giants will forever alter the local group's structure and the cosmic landscape. Their legacy will be written across billions of years in stars born and extinguished, in black holes merging and galaxies transforming, a deep reminder of the vast and vibrant cosmos of which our own galaxy is a part. This understanding sets the stage for contemplating the eventual aftermath and cosmic legacy that will define the fate of our galactic home and its companion in this epic celestial narrative. The grand cosmic drama culminating in the eventual merging of the Milky Way and Andromeda galaxies promises to be one of the most transformative events in the local group, marking the dawn of a new galactic era. This final chapter explores the aftermath, the birth of Milkomeda, and the cosmic legacy that will shape the landscape of the universe for billions of years. When the inevitable, or possible, collision unfolds, it will trigger a spectacular reordering of celestial structures. The graceful, ordered spiral arms that define both galaxies will be violently distorted by immense tidal forces. These forces stretch, twist, and compress the stellar and gaseous contents, producing grand tidal tails and bridges composed of stars and clouds of gas pulled from the disks. The interplay of gravity and motion will unleash chaotic shock waves through interstellar gases, igniting prolific bursts of star formation. These starburst episodes will seed the newly forming galaxy with a fresh generation of stars and planetary systems, intensifying luminosity in certain regions and creating a vivid cosmic panorama of birth amid destruction. Despite the apparent violence, the great emptiness between stars ensures that stellar collisions are extraordinarily rare. Instead, the merger will be a gravitational symphony. 2 billion stars, gas clouds, and vast dark matter halos interacting and remixing, reshaping the combined system's distribution and momentum. This enormous redistribution of stellar orbits will erase the well-defined spirals of the progenitor galaxies, ultimately settling into a massive elliptical galaxy. This descendant giant elliptical, often called Milkomeda, represents a mature endpoint in galactic evolution, where chaotic mergers yield smoother, more spheroidal systems. At Milkomeda's core lies another climactic event: the supermassive black holes at the centers of the Milky Way and Andromeda, each millions of times the mass of the Sun, will spiral ever closer due to dynamical friction against surrounding stars and gas. Over time, they will merge into a single, even more massive black hole. This momentous coalescence will unleash powerful gravitational waves rippling across space-time, a silent but energetic testament to gravity's ultimate dominance. The solar system's journey through this cosmic upheaval is uncertain but illuminated by sophisticated models. There is approximately a 50% chance that our Sun and its planetary entourage will be cast into a new orbit 3 times further from the galactic center than its current home. Even more dramatically, there is a roughly 12% chance that the solar system could be gravitationally ejected entirely from the newly merged galaxy, becoming a rogue system adrift in intergalactic space. However, even in these scenarios, the scales involved mean planetary systems remain intact. The vast distances between stars shield individual worlds from catastrophic collisions. While the Milkomeda merger marks a monumental change in galactic structure, it does so on a scale so immense that it dwarfs human and planetary timescales. The merger is predicted to occur several billion years in the future, far beyond any immediate or foreseeable human concerns. Long before Andromeda's tidal forces reach into our stellar neighborhood, the Sun itself will approach the twilight of its life, expanding into a red giant and drastically changing conditions on Earth, ultimately rendering the planet inhospitable. Thus, the galactic merger stands as a magnificent cosmic event that, while critical to understanding the universe's evolution, does not define the near-term fate of our home world. Beyond the immediate aftermath lies the far future of the local group. Over the coming 100 billion years, the combined mass of Milkomeda will dominate, attracting and eventually absorbing satellite galaxies and any neighboring companions. The local group's many galaxies will be gradually consumed, coalescing and smoothing into an even larger elliptical galaxy whose light will fade as star formation exhausts available gas. This marks the end of the spiral epoch and the dawn of a universe dominated by massive, quiescent ellipticals. Milkomeda's formation is a powerful illustration of hierarchical galaxy growth, a cosmic cycle of assembly where smaller galaxies merge to form larger ones, continuing over billions of years. It also highlights the interplay between baryonic matter, stars, and gas, and the invisible scaffolding of dark matter, within whose vast halos these processes unfold. Through its rich starburst history, complex internal restructuring, and eventual galactic metamorphosis, Milkomeda encapsulates the story of cosmic evolution writ large. In the grand narrative of Andromeda's journey, from a mysterious fuzzy nebula to a cornerstone of cosmic distance measurement to a dynamic spiral titan with a lopsided double nucleus, and now to a galactic predator with a violent past and uncertain future, the story culminates in the meeting and merging of two galactic behemoths. This event will reverberate through the local group and beyond, symbolizing the relentless progression of time and gravity's inexorable pull. Thus, Andromeda's cosmic legacy is twofold. It expanded human understanding by revealing the vast scale and plurality of galaxies and shapes the destiny of our own galaxy through a monumental collision. The future holds a majestic spectacle of cosmic transformation that will reshape the stellar and dark matter architecture of our neighborhood for eons. While its timelines stretch far beyond human existence, the echo of Milkomeda's creation will endure as a testament to the dynamic and evolving grandeur of the universe. This closing chapter sets the stage for contemplating humanity's place amid cosmic tides and enduring mysteries, inspiring wonder and humility as we gaze toward the stars that will merge and shape the fate of all nearby galaxies. The Andromeda story, intertwined with the Milky Way's destiny, stands as one of the most consequential tales in our quest to understand the cosmos, a tale written across billions of years and uncountable stars.